Welcome to the second video in our Class 14 series of lecture videos. We ended our first video with a discussion of relative rates for halogenated, in fact brominated, cycloalkanes in the SN2 reaction, and we saw that our fastest reacting halogenated cycloalkane was bromocyclopentane. Uh, the bromocyclopropane and bromocyclobutane were fairly slow in terms of relative rate. Our bromocyclopentane, we established, had a relative rate of 1, which was comparable to isopropyl bromide, and even our favorite six-membered ring, our bromocyclohexane, was a slower reacting electrophile in the SN2 reaction with a relative rate of 10 to the minus 2 because our nucleophile interacts with the axial hydrogens in the low energy conformer of our bromocyclohexane ring, and that steric interaction slows the reaction rate. So, to rationalize relative rates, we need to consider transition states or use Hammond's postulate. For the cyclopropyl and cyclobutyl rings, strain develops in the transition state from small ring size. This raises the activation energy and slows the reaction rate. For cyclic electrophiles, one needs to consider strain versus conformation and the sterics. As we pointed out, the axial hydrogens in the low energy cyclohexane conformation of bromocyclohexane posed a challenge to our incoming nucleophile. So how about leaving groups? We'll continue in discussing our parameters for our SN2 reaction. Leaving groups are a big parameter. Here we've got a general equation for our SN2 reaction. We have some nucleophile coming in, attacking some sort of hydrocarbon that has a leaving group X. Could be a halide, could be something else. In an SN2 reaction, we do our substitution. Now we have the alkyl group bonded to our nucleophile, and we have X minus. Well, if we're a halide, let's consider HF, HCl, HBr, HI. There is increasing acidity as we go down the column in the periodic table from fluorine to iodine. HF is actually a weak acid, whereas HCl, HBr, and HI are very strong acids. Iodide is the most stable in most solvents. It's got this formal negative charge. It's sort of spread out over a larger surface area. Iodide is kind of fluffy compared to these other anions. Bromide's still a nicely spread out charge, so is chloride. And these are much more stable as conjugate anions than fluoride. Fluoride is actually a weak conjugate base. So our best leaving groups in the halogen series are iodide, bromide, and chloride. We won't see fluoride serving as a decent leaving group in that series of halogens. What about other leaving groups? Well, we want to look for the conjugate base of a strong acid, because that means that base is stable in most solvents. So it's important to also recall that the stronger the acid, the weaker the conjugate base. Strong bases aren't good leaving groups for the SN2 reaction. And so let's take a look at what these types of groups might be. Sulfonates. These are good leaving groups. So we have an alkyl group bonded to a sulfur that's bonded to 3 oxygens. In fact, when that oxygen is bonded to a hydrogen, it's a sulfonic acid, which is a fairly strong acid, sort of close to H2SO4, but maybe not that strong. Here we've got a nucleophile attacking some sort of sulfonate that's bonded to this ethyl group, and our nucleophile attacks the carbon and it kicks out this sulfonate anion. What can those R groups on the sulfur be? Well, we could have tosylate, that's a paramethyl benzene ring. We could have a mesylate, so the R group is methyl attached directly to the sulfur, or we could have a triflate, so the R group is trifluoromethyl. We abbreviate the tosylate TSOR, we abbreviate the mesylate MSOR, and we abbreviate the triflate TFOR. So in addition to our three good halides, chloride, bromide, and iodide as good leaving groups, we have these sulfonates as decent leaving group. Interestingly, triflate should be a better leaving group than mesylate because triflic acid is going to be more acidic than mesylic acid because the fluorides are more electronegative than the corresponding hydrogens on this methyl group. They pull electron density out of the carbon, which pulls it out of the sulfur, which pulls it out of the oxygen, which allows the oxygen to stabilize that negative charge and make it a more stable conjugate base once the triflic acid has given up its proton. So, continuing on, at the beginning of our Class 14 first lecture video, we looked at the reaction of hydroxide. We considered the reaction of hydroxide with ethyl bromide. So we discovered that was spontaneous. So how about the reverse reaction? Can bromide kick out hydroxide? Does hydroxide make a good leaving group? And so hydroxide is a relatively strong base. So it's a terrible leaving group. The reaction is favored in the reverse direction, the direction that we considered it at the beginning of our first video of this series. However, we can find some conditions that will work, acidic conditions in fact. So let's take this propyl alcohol, and instead of throwing in sodium bromides and trying to have bromide kick out hydroxide, let's throw in HBr. Well, HBr is a strong acid. It'll ionize in a polar protic solvent, so we can go ahead and protonate our hydroxyl group. We'll draw an arrow double-headed from one of the lone pairs on that hydroxyl group's oxygen to this hydrogen of our HBr, and we'll form something that kind of looks like water, right? And of course, a bromide anion. This is our protonated hydroxyl group. It's got a formal positive charge. Even though the oxygen has the formal positive charge, oxygen's still more electronegative than carbon. So carbon still has a delta plus character. Our bromide then attacks that carbon. And now instead of kicking out hydroxide, it kicks out water. Well, is water a strong base? And the answer is, on the relative scale of things, no. So it's much easier to lose water as a neutral leaving group than hydroxide. So this is allowed, and this is an SN2 mechanism. And I'm sure we'll be tested on it at some point in some place. And I think that pretty much, does it for this lecture video.